Two quick printouts that I forgot to bring on Monday. So when I talk about how there's a million different types of transistors and we're only talking about two, right? And I said you could go look this diagram up on Wikipedia, or this is a scan from a textbook. So we, out of this diagram specifically, last time we talked about NPN bipolar junction transistors, right? So you see I talked about how there's the reverse type of that, PNP. And today we're going to start talking about field effect transistors. So you see there's all these things with FET in the acronym. And we are specifically going to talk about, if I can find it, N-channel enhancement mode MOSFETs. And what we'll see is these are kind of conceptually similar or analogous to the NPN BJTs. They're basically, if you turn the control pin on, send a high voltage or high current to the control pin, then it turns the load current on. A lot of these other ones, kind of you see how the arrow is pointing in the other way, kind of work in the opposite direction where it's off by default when this voltage is high, and then this part turns on when this voltage is low. And so we're not worried about the like maze of what exactly all these different arrows mean. Just going to talk about these two kind of common types and their analogous behavior, and then you're going to use them on the homework if you haven't started that already. Okay? And then I also had just meant to bring this last time when I was talking about MOSFETs and the heat sinks. Right, so if you haven't picked it up already, this is not to scale, but the MOSFET you'll have in your kit, or you need to pick up in lab because it wasn't included in your kit, looks like this, right? And there's this big tab with a hole on the back. That hole is there so you can bolt a heat sink onto it. Okay, so again, a lot of you are taking heat transfer right now. I don't know if you've gotten to convective cooling, okay? Yeah, so have you done any like homework problems with fins? Okay, so lots of fun, right? But that is, again, tiny little surface area here, maybe not enough to dissipate all the heat. Bolt a bunch of fins on there and it lets it dissipate more heat. So again, I mentioned last time, we're not talking about the super tiny atom thick billions of transistors in an Intel processor, right? We're talking about these big things that you can use to control motors. Okay. So, talking about MOSFETs instead of BJTs now. So MOSFET is quite a mouthful. MOSFET stands for metal oxide semiconductor field effect transistor. And again, there's lots of interesting material science about all the semiconductor physics stuff, so we don't really care about what the metal oxide part of this means. We're just going to call them MOSFETs. And again, we are specifically talking about N-channel enhancement mode MOSFET. So that's the giant alphabet soup of acronyms and terminology. So just kind of have that in the back of your mind if you're out there in the world after this class and you see like, oh, this is a P-channel MOSFET or a depletion mode MOSFET instead of an enhancement mode, then you need to go double check kind of this job, figure out which one that is and how does that one work, because it's not going to be exactly the same as the one we talk about here. So the N-channel MOSFET is going to have 3 pins similar to the BJT. The symbol looks like this, where we've kind of got a bunch of little lines inside. I'm going to zoom in actually just so you can kind of see this one a little better. And we've got an arrow pointing kind of to the left on the middle line there, so I didn't draw that perfectly, but you got the idea. And we're going to have 3 pins, the drain D, the gate G, and the source S. So that is analogous but not identical to, remember when we saw the BJT, we had the collector C, the emitter E, and the base B. So in the circuit diagram, the analogous pins line up. Okay, so the base is analogous to the gate, the source is analogous to the emitter, and so on. Where in this case, a voltage applied at the gate is going to control a current from the drain to the source, but there's no current into the gate. This is voltage controlled. So remember, for the BJT, we had the base current, and then in the active mode, the collector current was proportional to the base current. for the MOSFET, the gate current equals 0. Okay, so this current ID is going to depend on the gate voltage. Now, again, in the circuit diagram, the analogous pins line up. That is not true for the physical part. Okay, so if you build your BJT circuit for the homework, just yank out the BJT and pop the MOSFET in its place, it will not work. You need to look up the pinout on the data sheet. Remember, so I do not have this memorized, so I'm not going to write it down in the lecture notes here. But you have 2 different packages. They each have 3 pins, but I think, for example, on the BJT, the base is the middle pin, and on the MOSFET, the gate is the left pin. But don't quote me on that. Double check the data sheet. Okay, so look up pinouts on the data sheet. They're not physically interchangeable when actually doing this on a breadboard. Okay. So I'm going to zoom back out. When connected to an external load, the setup is going to be pretty much the same as what we had with the BJT, where you're going to have your load resistor RL connected up to your power source, which you might see labeled as VDD instead of VCC for a MOSFET, since it's connected to the drain pin there. But again, subscripts are going to be different wherever you look. Different people's lecture notes, different textbooks, different websites. So make sure you understand, or double check, like, okay, that's my power supply, positive 12 volts or whatever it is. And you may still have, even though there's no current into the gate, you might still have a gate resistor, call that RG, between your control voltage and the gate as a kind of backup to protect your control voltage. So if this is an Arduino pin, and if there's no resistor here and I accidentally blow up my MOSFET somehow, right? If this MOSFET fails short and this resistor is not here, then I've shorted my Arduino pin to ground, which is bad. That's going to damage my Arduino pin, right? So even though there's no current here, that current is still 0. You may still see that gate resistor there just as kind of a safety backup. Okay, but it will work without it. You can just wire an Arduino pin directly to the MOSFET gate and use that to turn something on. It's just not necessarily the greatest idea in case something bad happens. Okay? So this thing is going to turn on when the gate voltage, so VG, VD, VS, I can measure the voltage of each one of these pins relative to ground. It's going to turn on when the gate to source voltage, so in this case my source voltage is 0, so that's the same as just asking what my gate voltage is greater than some threshold voltage. So in the data sheet you'll see that as VGS comma TH for threshold. And if you look at a graph of that, which is what you're going to be producing for the homework, it's going to look kind of more like what we saw for a diode, where basically the voltage, the current through the drain is 0 for a while until you cross that threshold voltage, and then the current's going to increase really rapidly, and eventually will kind of level off again. Okay, so similar, again, conceptually similar to what we saw for the NPN BJT, where we basically have a cutoff region where everything is off. We have we'll talk about this more in a second, it's actually more quadratic here than linear, but kind of a region, this isn't perfectly vertical, it's not just on and off, there's kind of some in-between region where the current can increase, and then eventually it's just gonna flatten out again based on kind of what your power supply and resistor values are. Yes?
Is the BJT that's drawn to the right and then the diagram to the left with the drain source and gate, are those for comparison, or are those 2 modes of the same thing?
No, so that is for comparison. So this is what we talked about last time?
Yeah.
Okay, so that is kind of to have a side-by-side comparison of the 2 circuit symbols and the analogous pins. But they are 2 physically different pins. Okay? So again, the analogous pins line up in the diagrams, but not on the physical pad. So like the gate is your control pin, right? For BJT, the base is your control pin. and then the drain or the collector would be connected to your load. Like, so we had a similar diagram for this for the BJT last time, and the source or the emitter is connected to ground. Okay? So similar to the BJT, this is going to have different operating regions. Somewhat annoyingly, they have different names depending on which textbook or website you look at. So I'm just going to write down all of them. So first is called, depending on where you look, either the triode, linear, or ohmic region. And this is where it sort of acts like a variable resistor. So when it is just beginning to conduct, okay, then we have this complicated equation for the drain current as a function of K, which is called the conductance parameter. So for the BJT, we have the gain beta. Here there's just some different physical constant that kind of scales the current, times 2, times that gate source voltage minus the gate source threshold voltage times the drain to source voltage minus 1/2 times the drain to source voltage squared. So kind of a more complicated equation, but ultimately it's giving us the drain current depending on those voltages. And I had intended to squeeze this all onto one piece of paper, but kind of failed here, so I'm going to have to move up for one more and try and keep that there. And then after that we have what is, again, depending on where you look, either called the active or saturation region, which is kind of a confusing choice of terminology. I think there's actually a textbook that literally calls this an unfortunate choice of terminology, but because the saturation region of a MOSFET corresponds to the active region of a BJT, so then I think some people have decided, okay, well, calling it saturation is stupid, we're going to call it active instead. But then you have some textbooks that still call it saturation. You don't have to worry about it too much. Where we again have a slightly different equation, K times VGS minus VGS comma TH squared. So again, it's quadratic, not linear. And you see how in this one, there's kind of that extra VDS term in there. Here, this one, here it's been dropped. So point being, the drain current depends on the gate voltage somehow, right? As you increase the gate voltage, that current's going to go up. Okay. I wrote those equations down so you have them. I'm not actually going to make you use them on the homework, okay, because the analysis here gets a little more complicated with the quadratic equations and everything. The point is I want you to understand this behavior and how that corresponds, again, to the, so that's for the MOSFET. And if we kind of remember the BJT from last time, the axes of this graph were current, right? We had the base current and the collector current. And there was this linear region, and then eventually we kind of saturated and couldn't get any more current. So similar concept where, at the very beginning we talked about just kind of having a faucet or a control valve that you can tune to control the current to the load. For the MOSFET, that controls the voltage. As I change this voltage, I'm kind of going to go from off to on. For the BJT, that controls the current. As I control that current into the base, I'm going to have this linear current through the load, and then eventually it's going to saturate. Okay, so conceptually, you should understand the difference between current control and voltage control. And then that raises the question, like, okay, I can use both of these to control a load like a motor. Well, which one should I use if I have the choice? And that goes a little deeper into electrical engineering than we're going to get in this course. The very short answer is that MOSFETs are kind of a newer technology. I think there's a textbook called The Art of Electronics that is kind of one of the most well-respected textbooks in the field that says something like 90% of transistors in the world today are FETs. Okay, so BJTs are kind of an older technology, but they haven't gone away completely because there are certain things that they are better at than MOSFETs. Which again gets, when you're talking about temperature stability and noise and speed, we never talked about how fast, like if I switch the voltage at the gate on, how fast does the current start flowing through the load? There's all sorts of stuff like that that we're not going to get into. But in practice, if you're going to go control a motor, you're probably going to do it with a MOSFET and not a BJT. Another kind of advantage of the MOSFET is, remember, there's no current through the base. So even if I have this gate, sorry, no current into the gate, if I have this gate resistor here, there's no power dissipated in it, right? Whereas for the BJT, we always have to have that base resistor there, and for the load to be on, there has to be current into the base. So even though it's tiny, we're always dissipating some power in that resistor. So if you just want to leave something on, you're just continuously dissipating power in the base resistor, which isn't doing anything useful, whereas the MOSFET, if you want to turn this voltage on and leave it on, then there's no current here, and I just have all my current through my load. So that's a minor example of one of the differences, but again, that doesn't mean MOSFETs are better for literally everything. Okay. MOSFET questions. Again, if you haven't started already, you will be using one of them to build an LED driver and kind of compare the behavior to the BJT circuit on the homework that's due Friday. Nothing? Okay. So, getting to some of the more applied, okay, cool, why do I need to know that? What does it have to do with my robot project, or content, sorry. So, switch gears for a minute. Let's think about motors. Okay, just basic DC motor. We are going to represent it, so I'm just going to draw up a line there to DC motor. Okay, we're just going to represent that as a circle with an M in it. It has two wires, and if I just hook a motor up to a battery, directly to a battery, okay, current's going to flow through the motor, and it's going to spin. So I'm going to arbitrarily define clockwise and counterclockwise, right? So for this particular motor, if I hook up the motor's positive wire to the battery's positive terminal and negative wire to the battery's negative terminal, this motor is going to spin clockwise. If I reverse the wires, or reverse the connection to the battery, and so if I do this, okay, then the motor's going to spin the other way. And this comes from, if we talk about physics, right-hand rule, right? If you have current flowing through a wire, then the magnetic field curls around the wire. If you reverse the direction of the current, you reverse the direction of the magnetic field. Great, we're going to go into kind of the inner workings of DC motors here, although I believe you should have seen at least like one lecture about that in 2250, right? Kind of like cross sections of motors and what all the coils and magnets inside and stuff look like. See some head nodding and some blank stares, so maybe not remembering it that well. Okay, maybe I'll get I think Professor Hoffman sent me a slide deck for that, so maybe I'll pull that up next time as a reminder. But for now, take my word for it. There are lots of different types of motors out there. We are talking about the super simple DC motor, two wires. If you reverse the wires, the motor spins the other way. Okay. For you, if you want your robot to go in reverse, right? It's one thing if you want to build a robot that can only drive forward. Maybe you could pull that off, but probably not going to have a good time in the competition if your robot can't go backwards, right? So that is our motivation. How do we reverse the direction a motor is spinning without having to reverse the connection to the battery, right? You cannot, in the middle of the competition match, go in there and unplug the wires and swap them to make your robot go in reverse. So how do we do that with hardware and eventually with software? Okay, that is the motivation for the rest of today, depending on how far we get. All right, so one way to do that would be to say, okay, I'm going to have a circuit with a switch and two different batteries with different polarity or different orientations, right? So if I have my motor like this, so if the switch this is a toggle switch that can toggle between two positions, like the slide switch you have in your kit, right? If my switch is over to the left, then okay, current's going to flow through the battery one way. Great. And if I toggle my switch over to the right, then okay, current's going to flow through the battery the other way, and I've reversed the direction of current through the motor. Okay, that would work, but that requires two batteries, right? Ideally, I want to do this with just one battery. So how do can I reverse the direction of current through a motor with a circuit that only has one battery or one power supply? Okay, and we are going to do that with something called an H-bridge. Okay, so bear with me for a minute as I draw this. So I'm going to have some power supply I'm just going to call V+. That is going to go to a switch. That is going to go to another switch. That is going to go to ground. I'm going to connect my motor in between the two switches like that, and then I'm going to do the same thing on the other side. Power supply, so that's the same power supply. Switch to ground. So you can see where the name comes from, that if the switches were all closed, this would kind of look like an H. Okay? And I will draw out each case, but you can probably visualize what's going to happen if I close diagonally opposite pairs of these switches. Right? So if I first close this one, leave this one open, leave that one open, and close this one. Okay, great. And I have a path from power to ground with current flowing left to right through the motor. Right? And let's say, again, for our example motor here, that's going to make the motor spin clockwise. If I reverse that, leave this switch open, close this one, close this one, and leave this switch open. Okay, I have reversed the direction of current through the motor, right? And now I have a path from power to ground that way, and my motor is going to spin the other way. Okay, so just by controlling these pairs of switches with a single power supply, so I didn't draw them connected, right? But these V pluses are coming from the same battery. I can reverse the direction of current through the motor. Okay, you may think or ask, okay, well, what happens if you close all the switches on one side and leave the other side open, like this? Okay, well, that is bad because now I have a short circuit from power to ground. Okay, so don't do that. That is bad. Okay? So that is with mechanical switches, right? Again, you're not going to reach into your robot in the middle of the competition and toggle switches to control direction through the motor. We want to do that electronically, so we can do that with transistors instead. Instead of switches, if we have 4 transistors,
lower mobility.
whether they're either BJTs or MOSFETs, right? So I'm just going to draw a generic. I'm not going to fill in the inside there. I'm just going to draw kind of a generic circle representing the transistor, because in both cases we still have a control. We have a control pin, and we kind of have pins that the current flows through for the load, right? So those are transistors. Okay. Now I can turn those on and off electronically with my control signals, right? So this is a control voltage, and I didn't draw. If these were BJTs, I would need the resistors on the base. If they were MOSFETs, it would still be a good idea to have the resistors on the gate. So I didn't draw that, but I have 4 different voltages I can control to turn these switches on and off, right? And I could, if I wanted to, reduce that to actually, there's 2 control voltages. I could say, okay, I'm going to link this one to this one because those 2 should always be on at the same time, right? So I can have a single voltage to control those. And I could link this one to this one, right? So that way I only have 2 control signals I need to send for which way I want the motor to go. So if I want the motor to spin one way, I made the red voltage high and the blue voltage low. If I want it to spin the other way, I flip that, and if I don't want it to spin at all, I just make both voltages low, right? And if I make both voltages high, then I have a problem because then I'm doing this. I'm short-circuiting it, okay? Is that clear? So, yes?
The connection between the control voltage to the house, they're not that.
Sorry, can you speak a little louder? I heard the connections between the control voltages and I didn't hear the back part.
They're just not that clear.
Okay, let me draw. I'm just going to redraw this last one bigger on a new piece of paper because it's getting a little crowded in there. Okay, so bigger version with transistors. Okay, B plus, B plus. I have, and actually I'll do it with BJTs as an example, so we have the base resistors in there, but you could also do this with MOSFETs. So we have a BJT there. I'm going to attempt to draw this one mirrored. BJT there. There's our motor. Another BJT here to ground. Another BJT here. Drawing these backwards is hard. Hold on. There we go. Okay. Another BJT there. Okay. So I could have 4 different control voltages here, right? Let's call it V1, V2, V3, and V4. Okay, but I'm only ever going to turn them on in pairs, right? So these 2 would turn on at the same time, and these 2 would turn on at the same time. Okay, so I could connect, I'll draw it without the lines crossing this time. This one, I guess I can't draw it without the lines crossing, but those 2 could be connected and just be a single control voltage, and these 2 could be connected and just be a single control voltage. Does that make more sense? Okay. So when it comes to using the Arduino, basically I don't actually need to use 4 pins on the Arduino. I can do it with just 2 to control direction. But you are not going to build this yourself with 4 discrete transistors. Okay? You can just go buy an integrated circuit that has all of this stuff inside it already. So that is what you're going to do in lab 3 and when you build your robot. Okay, so there are many different types of H-bridge ICs out there. So this is another case where you need to look at the datasheet and look at the pinout for the one you have. But the one we are going to use in this course is called the L9110 H-bridge. So this is the part that I mentioned a while ago. If you just glance in your kit, it looks like you're opping it, right? It is an integrated circuit with 8 pins. It's got the little kind of half notch on one end so you know which side is the top. And if you go look in the data sheet, those pins are going to be labeled 0A, VCC, VCC, or sorry, that's a O, not a 0, OB, GND, IB, IA. I don't know if I have B and A switched there. I hope not, but you will double check the data sheet before you do it yourself, and ground. Okay? The data sheet is also going to tell you, okay, well, what do those labels mean? VCC, we've seen, means power. GND, not surprisingly, means ground. Okay, I is your input. That's going to be your control signal from the Arduino. So that has both A and B. And then O is your output. That's the output to the motor. Also A and B. Okay? Now, you'll notice that there are 2 power pins and 2 ground pins, which might seem electrically redundant. That's to help dissipate heat. Right? Again, motors draw a lot of current. They're all taking heat transfer right now. If you have 2 pins that are physically connected to the underlying circuit board or breadboard, that's double the path for heat conduction, right? So you'll see that there's one in Tinkercad you'll see that actually has 4 ground pins, right? So you know this little chip in your kit does not have a heat sink mounted on it, but you can look in the data sheet and say, okay, what's the maximum current rating that this thing can handle? And if you exceed that, then you're going to, you know, by applying too much voltage or trying to use it to drive a motor that's too big, you're going to fry it. So these are fine for the relatively small motors you're going to use to build the robot, but they, you know, you wouldn't find these in an electric car. Okay? So again, the inputs are from the Arduino. The outputs are going to be 2 the motor. Okay, and then there's other nice things you get with an integrated circuit, like built-in flyback diodes. So we talked about flyback diodes a couple lectures ago and how they help protect other components of the circuit from damage due to suddenly shutting off an inductive load. This circuit on its own doesn't have that, right? I didn't draw any diodes here, so if I shut these voltages off abruptly, that's potentially going to blow up my transistors. You could build this yourself with individual transistors and individual diodes, but if you just go buy an H-bridge integrated circuit, a lot of times those diodes are just going to come inside there and you don't have to worry about connecting them externally. But you need to check the data sheet because that's not always the case. Okay, so it is the case for this one, but if you go do some other project and just buy an H-bridge, you need to check if the diodes are included or not. Okay, the data sheet is going to give you a table that tells you what the outputs are based on the inputs. Okay, so the table will look like this, where the columns are IA, IB, OA, OB, and if IA is high, then IB is low. So basically, if the corresponding input goes high, then the corresponding output also goes high. Right? If input A is low, input B is high, and output A will be low. And when I say high and low here, I'm talking about voltages. Right? So coming from the Arduino, that's going to be either 0 volts or 5 volts, which we'll talk more about starting on Friday. Going to the motor, that's going to depend on what VCC is. For example, if you're controlling a 12-volt motor, then when that goes high, that's going to be 12 volts, not the 5 volts. So this also, again, when we started talking about transistors, we talked about how this lets you control a higher power load with a lower power signal. So this lets you use an Arduino, which can only output 5 volts to control, say, a motor that's 12 volts or something higher. Okay? And then if both inputs are low, then both outputs are just low. And I guess we should also add a fourth column here for what does the motor actually do. So there, again, I'm kind of defining clockwise and counterclockwise arbitrarily. If everything's low, it just doesn't spin. And the other nice thing about the integrated circuit, it contains internal protection to help basically prevent you from doing this case. If I turn all the inputs on, when I did this manually, then I would have a short circuit from power to ground. It prevents that from happening. So you can set both inputs high and it's still just going to stop the motor. It's not going to blow things up in short power to ground. Okay? The data sheet will also have a diagram showing the typical external connections. And the version in the data sheet looks like this. And this has tripped people up in the past. So these little flag symbols represent Arduino pins. We'll see those more as the semester goes on. So remember, I can't remember what lecture this was. I talked about the different conventions for drawing whether wires connect or cross. So the data sheet for this part uses this convention where a dot means the wires are connected, and overlapping like this just means they cross without an electrical junction. Okay, so people doing lab 3 the last time I taught this looked at this and thought, okay, that means we're just supposed to connect one end of our motor directly to power because of that, and we connect both of our Arduino pins directly to ground because of this, and then your circuit just won't do anything, right? Because you're shorting your Arduino pins to ground, which is going to damage them when you set them high, and one end of your motor is just always on. So those are not connected, those points. Okay, so do not make that mistake when you go to do lab 3. Okay, H-bridge questions. And then, so this allows you to control the direction of one motor, spin it forward and reverse using 2 Arduino pins. Your robot is going to have 2 motors, right? 2 wheels, so you will use 2 of these, and then that allows you to let your robot steer, right? You have 2 wheels, so your robot doesn't have a steering wheel like a car, right? It's not changing the angle of the wheels, it's just using 2 wheel called tank tread steering, right? So if I want to go forward, I spin both wheels forward. I want to go backward, I spin both wheels backwards. If I want to turn, I spin one wheel forward and one wheel backward. Okay? So lab 3 is going to kind of, you're getting to the point where you're starting to build the building blocks that you're then going to need to make the robot. Yes, in the back.
So is this only relevant in terms of like the direction in which the motor spins, or does it also have anything to do with controlling how much current that it will vary the amount of current that you're supplying?
Excellent question. So the question was, does this only, is it only relevant for controlling the direction the motor spins, or does it also vary the amount of current through the motor? So we are skipping ahead, but a preview of something we're going to cover in a few weeks. So the Arduino pins that are controlling this are digital, so they can only output a high or low signal. So they can only be 0 volts or 5 volts. So you cannot continuously vary the current through the motor to control its speed, but you can use something called a PWM, which stands for pulse width modulation signal, where basically you turn the digital pin on and off really fast, and the amount of time that it's on corresponds to the motor speed. So if it's, the amount of time that it's on is called the duty cycle. So if it is just off the whole time, that's 0%. If it's on 25% of each period and off 75% of each period, that's a 25% duty cycle. So on 50-50, it's a 50% duty cycle. There's 75, and so on, and then 100% is just on the whole time. So this allows you to use a digital pin to control the motor speed. It's actually similar to how LED light dimming can work, right? So sometimes we're not actually controlling the amount of current flowing through the LED, we're flickering the lights on and off faster than the human eye can see, right? So if it's on half the time and off half the time, but that's, you know, if I do that once a second, right, that's slow enough that I can see it. But if it's faster than the human kind of vision response time, the effect is that the LED looks about half as bright. So same thing for motors. You kind of have to, this signal has to be fast enough to get a continuous speed out of the motor, right? If I turn it on for a whole 5 seconds and turn it off for a whole 5 seconds, then it's just going to go full speed, stop, full speed, stop. But if I change this voltage really, really fast, then I can actually control the speed of the motor. I'm glad you asked that question. Because that also kind of ties back into this graph where, yeah, for BJTs, okay, we kind of have this linear region, but to do that, I need to be able to vary this voltage, right? Which again, I can't do with an Arduino. It's either 0 volts or 5 volts. So I'm pretty much either going to be off or saturation. And then same thing for the MOSFET. I kind of have this narrow band where, yeah, I could control the current, but that would require a really precise voltage, which I don't have with the Arduino. It's either 0 volts or, so it's either going to be off or on. So it is, well, in theory, you could build something to control the current through a motor by doing something with transistors to kind of get a more precise current value. In practice, most microcontrollers just have digital pins, so it's way easier to do it with PWM. Okay. Other H-bridge questions? All right, we actually for once got through that faster than I thought I would, so that does not mean you get to leave early. It means we're going to start the stuff for next time. But you may have noticed I didn't do any poll everywheres yet. Do not respond to the one I'm activating right now, okay? If you're in the room, don't respond to this one. Don't text your 2 friends who aren't here and just responded to it. Don't get yourself like, I really just don't want to have to deal with this, come on. Play, like, or if you're like in here, if you see somebody with like who has headphones on or is like replying to the poll even though they're in this room, like poke them and stop them. I don't want you to get in trouble if you're here. But if you are in this room, do not respond to the poll that is live. I was hoping this wasn't an issue anymore, but. And that was like fluctuating, so I don't know if some of you are changing your, like in the room and responding and changing your minds. No idea. I'm going to close this in 5. Again, if you're in the room, please don't respond. Just leave it blank. Make my life easier to sort this out separately with people who aren't here. 5, 4, 3, 2, 1. Okay, I will deal with that separately. If you are here, just answer D to this question. Okay? There is no graph. That is just a dummy question. Just answer D, you get the credit for today. Right. And since we didn't really do any kind of mathy type problems, there weren't really any good questions I could actually do today. So just answer D, please. Okay, 10, 5, 4, 3, 2,
Oh, 1 second,
1.
6. This phone's not loading.
Okay. If everybody good? No. Okay, we'll tell you. If I can see that you are here, so come talk to me after lecture, and I will write it down if it's still not loading. Or anyone? Okay.
You got it.
Okay, good. All right. Is anybody still having like pull everywhere loading issues? Okay. I see one hand in the back. All right. If you couldn't get it to load, come talk to me right after class, and I'll make sure you get the credit for it because I know you're here. Okay? Deactivate. All right. So we are going to start with a preview of what we are going to do on Friday in the last kind of 10 minutes here. Let me find the right PowerPoint. Clicky thing.
Excuse me,
Oh, I
Professor.
don't know the HDMI cable plug in, that'll probably help. Yes.
We had a question.
Sure.
Thank you. Sorry if I missed this. Is the L9110, is that a MOSFET or BJT?
I would actually need to check the datasheet. I assume it's FET. Just because, again, I think most motor drivers or H bridges you go by now are going to be MOSFET and not BJT, but honestly, I would need to double check the datasheet to be sure. I guess that doesn't change the external functionality or the pinout because it kind of just black boxes all of it for you, but the datasheet's on Canvas, so we can look that up. All right. Again, totally switching gears now, so like this might be a little mentally jarring of a transition, but so we've been talking about all this circuit stuff. We just kind of build up to, okay, how do we control a motor? You know, you need to understand resistance and inductance and transistors and all that stuff. You also need to program the robot, right? We want to control circuits with software. And in this class, we are going to learn to do that with something called registers. So I asked this maybe on the very first day of class, how many of you have done this before, okay, with an Arduino? So blinking an LED, just really basic blinking an LED type stuff, or at least like this looks vaguely familiar to you, right? Even if you took Python or MATLAB, the Arduino language is designed to be super beginner friendly, so people who aren't engineers, artists, kids, whoever can learn to do this stuff, right? Which is great and accessible. And you can kind of just look at this, and it has English command words, right? That if I tell you, okay, pin mode output, I say that is, this line of code is setting pin 11 as an output, right? That I can then turn on and off. So digital write 11 high, that is setting the voltage on pin 11 to 5 volts. Digital write 11 low, that is setting the voltage on pin 11 to 0 volts, right? So if I wanted to do that, or use that to control something like a transistor, to drive a motor, or blink an LED on and off, cool, I could do that. Great. So if you've done that before, you are not allowed to do it in this class. Do that and you get a 0. I am not exaggerating. This is going to be one of the things I say on camera, and then if somebody complains about it, I'm going to reply with a link to this video. Do not do that, you will not get credit. Okay? In this class, you're going to learn to do it like that. Okay? It looks more painful. It's a bunch of 1s and 0s. It's all in binary. But this is one of the, I think, major things that differentiates you as a Cornell engineer who took this class from everybody else out there who learned how to use an Arduino. Okay? All of the free stuff on the internet is like this. Most mechatronics classes at other universities are like this. It's great. It's easy. It doesn't teach you what's actually going on under the hood in a microcontroller, and this does. Okay, so this also ties into the eCornell version of the class. So the target audience for eCornell is mostly mid-career professionals and not college students. I repeatedly have people who took that class come to me and go, oh, I was in a meeting today and I knew what an interrupt was. Okay, I knew what a register was. I knew what a timer was. All of these things that the kind of beginner-friendly Arduino language hides from you intentionally because they don't want you to have to worry about it. So I'm giving this motivational pitch because this is hard, okay? It was hard for me to learn the first time. I had never done that before the first time I taught this class. And students kind of grumble about it because it's hard and say, oh, I already know how to do this, why can't I do that? Okay, again, you are probably paying a lot of money to go here, and you should probably get more out of this than what you could just go find for free on YouTube. Okay, so that is the introductory motivation for why we're going to do that. There are also some other practical considerations. For example, if I just blink an LED on and off, okay, so if I take these two programs and remove the delays, right, this code is just turning an LED on for a second and then turning an LED off for a second and repeating that in an infinite loop, so literally just blinking an LED. If I do that and remove the delays, okay, the blink with the Arduino commands, it takes 924 bytes of memory, and if I remove the delays and hook up an oscilloscope to look at those pins, okay, so what's the voltage on that pin? There's roughly a 4 microsecond gap between the rising edge and the falling edge. Okay, so that seems pretty fast, right? If I do it with registers instead, it's about 60 nanoseconds. Okay, so this is, I don't remember, more than 100 times slower. This is so fast that you can actually see the RC time constant curve on the Arduino pin, right? We are zoomed in so far that you can see that, okay, that voltage, I didn't hook up an external capacitor, there's just a little bit of capacitance on the pin that takes time to charge up. And whatever, the actual program itself is almost 10 times smaller, whatever it is. So when Arduino is great for prototyping, if you're kind of going out there in the real world and you want to go work for NASA or SpaceX or whatever, people aren't writing production code in the Arduino language, okay? And you might, as a mechanical engineer, not be the one writing the code, but again, you're going to be in meetings or working on a team with the people who are, in kind of the big company case, or if you're in grad school in a robotics lab, you might actually be writing the code yourself. So I forget, again, I hadn't actually planned to get this far today, so I don't have the rest of this lecture prepared, but basically what we are going to do starting on Friday is bring laptops, and we are going to be interactively working through learning all the bits and pieces of this in Tinkercad. You will be creating your own library of circuits in your account that you can then go look up when you need to know how to do stuff, which is going to be useful when building the robot. Okay, so all of this isn't kind of just theory for the sake of theory. I didn't say I was done yet. Hold on. Let me get off my soapbox. Give me like another minute, and then you can go. The goal here is that you are going to have things that you can refer back to for, okay, I need to do this for my robot. Where do I have this piece of code or this building block? But we're going to diverge, right? You're all going to break up into teams. You're going to have different strategies for the final project. So it's going to become more open-ended, but I want you to have the foundation to do it, okay? So don't forget laptops on Friday. Assume you need to bring them going forward. As usual, I will be here after class for questions, all right? Thank you.